All right, competitors, welcome back to Blackboard AI, where we simplify the toughest algorithms so you can conquer those coding challenges. Today, we are unraveling a classic, elegant, and absolutely crucial algorithm that appears in countless variations: Kadane's algorithm. What problem does Kadane solve? It is the maximum subarray sum problem. Given an array of numbers, both positive and negative, your task is to find the contiguous subarray within it that has the largest possible sum. For instance, take this array: -2, 1, -3, 4, -1, 2, 1, -5, 4. Can you spot the subarray that gives the maximum sum? It has to be contiguous, meaning elements next to each other. That is truly optimal. As you add a new link, a number, if the current chain becomes a burden, its sum goes negative, it is better to just cut it off and start a brand new chain from the current link. Why carry dead weight? But always remember the longest, strongest chain you have ever built, no matter what happens to your current one. Let us formalize these steps. Here is the Kadane's recipe. First, we initialize current max ending here to 0. This variable will track the sum of the best subarray ending at our current position. Second, initialize global max so far to the smallest possible number, like -infinity or intmin. This ensures any valid positive sum will immediately replace it. This is crucial for handling cases with all negative numbers correctly. Then, we iterate through each number in our array. Inside the loop, for each num, we update current max ending here. It is the maximum of either starting a new subarray from num itself, or extending the existing current max ending here by adding num to it. And crucially, we update global max so far. It is simply the maximum between our current global max so far and the current max ending here we just calculated. Finally, after the loop finishes, global max so far holds our answer. Time to see Kadane's in action. Let us use our example array: -2, 1, -3, 4, -1, 2, 1, -5, 4. We start with current max ending here equals 0 and global max so far equals -infinity. Global max so far equals max -2, 1 equals 1. Index 2, element is -3. Current max ending here equals max -3, 1 plus -3 equals max -3, -2 equals -2. Global max so far equals max 1, -2 equals 1. Index 3, element is 4. Current max ending here equals max 4, -2 plus 4 equals max 4, 2 equals 4. Global max so far equals max 1, 4 equals 4. Index 4, element is -1. Current max ending here equals max -1, 4 plus -1 equals max -1, 3 equals 3. Global max so far equals max 4, 3 equals 4. Index 5, element is 2. Current max ending here equals max 2, 3 plus 2 equals max 2, 5 equals 5. Global max so far equals max 4, 5 equals 5. Index 6, element is 1. Current max ending here equals max 1, 5 plus 1 equals max 1, 6 equals 6. Global max so far equals max 5, 6 equals 6. Index 7, element is -5. Current max ending here equals max -5, 6 plus -5 equals max -5, 1 equals 1. Global max so far equals max 6, 1 equals 6. Index 8, element is 4. Current max ending here equals max 4, 1 plus 4 equals max 4, 5 equals 5. Global max so far equals max 6, 5 equals 6. And there you have it. After iterating through the entire array, our global max so far is 6. This corresponds to the subarray 4, -1, 2, 1. Let us quickly look at the code. It is incredibly concise, reflecting the algorithm's elegance. We initialize current max ending here to 0 and global max so far to intmin or ::m, to handle large negative numbers or all negative arrays. The long type is a good practice in competitive programming to prevent overflow. just in case sums get very large. Then, the loop iterates through each number. The two standard max calls directly translate our logic. Current max ending here decides whether to extend or start fresh, and global max so far keeps track of the best sum found so far. Notice how this handles arrays with all negative numbers correctly. If the input is -2, -1, -3, global max so far will correctly return -1, because even if current max ending here resets, it will still capture the largest single negative number. The code is clean, efficient, and directly implements the algorithm. As we discussed, Kadane's is a winner in terms of efficiency. Time complexity, O(n) because we iterate through the array only once. Space complexity, O(1) because we only use a few constant variables, regardless of the input array size. This algorithm, or variations of it, pop up in surprising places. Think about problems like finding the maximum profit from buying and selling a stock. It is essentially a max subarray problem on price differences, or in image processing for finding the brightest rectangular region, or even in bioinformatics. Understanding this core idea unlocks many more problems. And there you have it, the elegant and powerful Kadane's algorithm. Master this, and you will find yourself solving a whole new class of problems with ease. Your homework: go implement this, test it with different cases, and try to find some variations of the problem. Practice makes perfect competitors. If this video helped you conquer Kadane's, hit that like button, subscribe to Blackboard AI for more algorithm breakdowns, and do not forget to ring the notification bell so you do not miss our next challenge. Keep coding, keep competing, and I will see you in the next one. Happy coding!